Let us start. Raghu, tell us about your career. How you ended up joining the energy markets, in special the solar PV market.
Yeah, happy to say that. My career has been a little atypical, I must say. So I have an engineering degree. I have a master's degree in electrical engineering. I also have an MBA from the Haas School of Business at Berkeley. I came to Silicon Valley back in 1993 after I finished my master's, and since then, I was just always fascinated by startups. And when you're in Silicon Valley, that's pretty much what you do is you look for opportunities in startups, and startups are a very interesting, they create a very interesting environment where there is so much focus on creativity and things that create discontinuities, if you may, in technology. And so my Enphase was my fifth startup. I started my career in a startup, and since then I've done a whole very varied set of different types of startups. I did the first one was in instrumentation. So I was working with a small group of people. We were developing laser-based scanning systems. The second one was in telecommunications, and that was a startup that was then acquired by Cisco. And I think that's the place where I developed most of my thinking around how I felt technology evolves over time, and it had the most impact on Enphase and the decision around Enphase. And that's where I also met my partner Martin, who I co-founded Enphase with. And by the way, that's where I also met Luciano for the first time. And then I went from that startup to, once we were acquired by Cisco, I enjoyed startups so much that I ended up going to an SSL VPN company. And then after that, I started my first company with Martin. It was in WiMAX wireless company in telecommunications. And then we started Enphase. So, in classic Silicon Valley fashion, I bombed the first startup, did very well on the second, bombed the third, bombed the fourth, and then here is Enphase, which is number 5. And it's been an amazing journey, particularly Enphase. From a technology point of view, right? I've been a technologist my whole career, and from how technology evolves, how companies evolve as a result of the baseline technologies is a fascinating observation, and I think a lot about it. And so that was the backdrop of how we started Enphase and the rationalization of why it made sense. And it was not obvious at the time what was going to be our value proposition. The whole thing around, hey, string inverters versus microinverters. Why microinverters was had a very rational grounding in technology, and I'm happy to share that with you. But that's been my career. I'm fascinated by technology, and I think and startups. Startups is not for the faint of heart, right? Startups are very hard, extremely hard. As somebody once said, if anybody knew how hard startups are, most rational people would not do it, right? So you have to be a little crazy to do startups, but it's also the most fun.
Right. And Raghu, as you were there since the beginning, tell us about Enphase, where it's headquartered today. If you can talk about this very beginning now Enphase, the first thoughts, and how you ended up being this giant company in the solar PV market.
Yeah, happy to share that. So today we are headquartered in Silicon Valley here in Fremont, California. We started the company just north of San Francisco, about 40 miles north of San Francisco, in a little place called Petaluma. And we were 2 guys and a dog. Martin's dog also was part of the team, and we were just the 2 of us. in a little room. We started with in his basement, just talking about, hey, what should we be doing? And the thinking was very rational, as I said. We had formulated these thoughts that if you look at how technology evolves, distributed architectures always win in the long run. They win for cost, performance, and reliability reasons. And there's a lot of existence proof of that. If you look at, mainframe computers to PCs, if you look at regular landline telephones to smartphones, right? If you look at even cars, etc., more and more intelligence gets pushed deeper into the network, right? The endpoints make more and more decisions. They're very intelligent. They make more decisions. They make more autonomous decisions, but they're all networked together. That's the common theme. The other common theme that runs through the examples that I gave you is digital technology, semiconductors, and software. So when we first started looking at solar, at the time it was all about solar, we saw that power conversion, everybody was focused, a lot of investment, venture capital investment was going on the panels, on the modules, right? There were a lot of people looking at thin film and other materials away from silicon, which I honestly, different story, but I think that was a mistake. You never bet against silicon. But some companies have been successful. If you look at for solar as an example, in utility scale, they do a good job with the cadmium telluride thin film material. But we were looking at the balance. We were looking at in balance of system, and in particular, we were looking at the inverter. And Martin and I were scratching our head, going, "Why is power conversion being done in a centralized manner? If our thesis was correct that distributed architectures always win in the long run, and there was all this existence proof, everybody should do micros. Micros make the most sense because you take what's ostensibly a centralized conversion and then distribute it, the power conversion down to an individual module." And then, of course, like every entrepreneur, the first thing we did was we sat down and did a lot of research, really understood, first why they didn't do it. It turned out people had done it before. People had done micros, 15 years before, but they had failed. So all of those micros had failed. And so then I dug in and I tried to understand why they failed. And here's the reason why they failed. The first thing was the way they made micros was they would take a big inverter, like a 5 kilowatt or a 7 kilowatt inverter, and shrink it down to 100 watts. And that was not the right approach. You really needed to re-architect in the microinverter from the bottoms up, right? What that meant was taking up, like I said, looking at history and understanding why things succeed, we had to say, okay, we're going to re-architect this as a digital topology. We're going to build our own custom semiconductor. All the controls was going to be in our own custom chip, which is what we designed. And we're going to make the whole device completely software defined. So which means we would write a lot of software that would define the performance of this device. And then we added a few more things. We said we were never going to design something that was just a piece of hardware. It was going to be software defined, and it was going to be part of a system. So it was just not about micros. It was about micros, full stack software, embedded communications technology, all network, a gateway, and a massive cloud infrastructure to support it. The communication was going to be fully bidirectional from cloud to device. So we were doing things like over-the-air upgrades, or IoT. We were doing IoT back in 2008 when people hadn't even formulated the word IoT. So our thinking was rooted in how technology evolves, right? And I think that is the core to our success. And now coming down to why is it better, right? If you just think about from a value proposition point of view, why is a microinverter better than a string inverter? There are 4 reasons. If you look at a string inverter, for example, right? Or a box inverter, as I refer to them, centralized inverters, the first one is you have a yield problem. The reason is the output of one solar module dictates the performance of the other because all the modules are connected or panels are connected in series. So the output of one dictates the performance of the other. If you have any shading, debris, anything, it's going to impact the whole system. Second problem, and arguably the biggest problem, is reliability. You're processing 5,000, 7,000 watts. You're switching very high voltage, 600 volts, 1,000 volts DC. So the stress on the components is very high. And so the unit itself is not very reliable. That's one. And second, it's a single point of failure. So if it fails, your entire solar system fails. It's not a distributed architecture, it's a centralized architecture. The third one is it's much more complex to design, install, and maintain. You have to think about things like string sizing, temperatures, location of these big box devices, etc. And most important of all, you're dealing with high voltage DC. High voltage DC is not normal, right? High voltage DC is a very esoteric voltage. It varies all over the place. There's no standard. And you need specialized components when you install a high voltage DC system. So there's a lot of training. So in some sense, it's every solar install is a custom install, right? So designing, installing, maintaining is much more complex. And finally, safety, fire safety. You have high voltage DC. High voltage DC, is prone to arc faults. If there's even a small problem with the connector system, you can ionize the air in between those connectors, and you generate a spark. And that spark can be thousands of degrees Celsius. And if there's any flammable material around it, you can start a fire. So when we came up with the notion of the microinverter system, because it was part of a system, every panel inverter pair or module inverter pair acts like an independent energy producer because you're doing a power conversion DC to AC at the module itself. So the performance of one has no bearing on the performance of the other, so you maximize output. The second one is we make these devices out of silicon, right? It's a semiconductor device. It's very, very reliable. Our failure rates are of the order of 500 defective parts per million. Other string inverters, and for that matter, even other micros, are orders of magnitude worse than us. The second thing, so the unit itself is very reliable. We're only processing a few hundred watts, 330, 335 watts. We are switching very low voltage, 40 odd volts. So the stress is not that significant. And most important of all, there's no single point of failure. If one of the module or the inverter were to fail, the rest of the system continues to operate. That's why we give 20 plus year of warranty on these devices, right? So you're much, much more reliable and you don't have a single point of failure. Third is you get 220 volts AC directly out of the device. So it's very simple to install, design, install, and maintain. I don't have to be coplanar. I can point the module in any direction. I can mix and match modules, anything. It's just a simple plug and play device. So anybody can install it. I know a lot of people. I saw a video even yesterday. Somebody saw a video on Enphase and did the install themselves, right? It's so simple. So especially in this environment that we are in today, where you're shortage of labor, you can train up people very easily to do an Enphase installation. It's very simple to install, very simple to design. You just surface area of the roof divided by the surface area for module, and that's how many modules you can put in. Very simple, all AC. And AC components are standard components. Everything is standard about AC. So designing, installing, maintaining is very, very simple. And finally, there's no high voltage DC anywhere in our system. All low voltage DC. So there is no danger or the danger of arc faults is significantly minimized. So it made complete sense to do a microinverter system. And now we have a full system. All our microinverters communicate back to Enphase. Just to give you a sense of scale, we have shipped 45 million microinverters to date. We are installed in more than 2 million homes. In the United States, every 30 seconds, an Enphase system gets installed. Every 30 seconds. And all of these systems are sending data to us. They send data about how the inverters are doing. They send data about how the modules are doing. We get data on how the grid is doing because we're all sitting on the grid. We get even, and now we get even, consumption data from the homeowners. We have an incredible amount of performance data, and that performance data actually informs us on how to provide better service to the homeowner, because it tells us about how our systems are performing. And so we can proactively, for example, call the homeowner and say, hey, it looks like you have shading, or it looks like you have a problem. Let's figure out a way to fix it, right? As an example. And so when we do find some stuff, more often than not, we can fix it in software. So we can do we do software upgrades remotely, and the system is up and operational again, or we have ways to improve the performance. We are on the right side of history. We are on the right side of history. When you think about it, when you look back and you think about Silicon Valley and you think about innovation and you think about technology, you're on the right side of history. Distributed architectures always win in the long run for cost, performance, and reliability reasons, provided you do it the right way. The approach has to be right. Architectures matter, right?
Right. Great. A lot of thoughts on that. I'm gonna explore this a little bit more when we were talking. But I want you, Raghu, to talk about this. You mentioned that a handful of other companies tried to develop the microinverter, and they were not successful on that. And you tell us about that. So can you tell that the very first commercial microinverter launched in the world was an Enphase microinverter?
No, it was the first commercial microinverter that was launched it was a bunch of small systems that people had done. I think they were experimenting. If I remember correctly, it was out of Denmark. And I think I remember looking at it, and I'll give you a little bit more technical details there. It'll help you understand. It was a very analog device. It was not a digital device. I think it was called OK for You. OK for the number 4 in you. And it was, I think a guy was playing with it. He had the right idea, but he had the wrong approach. And what they were doing, for example, was they were thinking about the problem as an analog problem. And when you think about an analog problem, this is where I was saying you take a big inverter and you shrink it down into something much smaller. You do things like a dual stage microinverter, which is, by the way, other microinverters I look around in the market are doing exactly the same thing. It's because they don't have the expertise in digital technology or semiconductors and software. So they take the easy route, which is I have to go from 36 volts, which is what a module or a panel puts out, all the way up to 220 volts AC. I do it in 2 stages. I do what's called a boost stage, which is a DC-DC stage, which boosts up the voltage to hundreds of volts. And then I do what's called a PWM stage, pulse width modulation. And then I turn that into AC because I chop up that DC and turn it into AC. That would be a very conventional way of doing it. For us, we don't do that. We do everything. We use high frequency digital conversion. Our converter operates internally at between 100 to 200 kilohertz, dynamically changing. We have a high frequency transformer. We started using silicon carbide. We used advanced materials. We are now looking at gallium nitride, which is yet again a very advanced material, wide band gap material. And then we do everything in our custom silicon. In fact, we don't even have a closed loop system. We actually run a detailed mathematical model of our converter inside our ASIC. ASIC means application specific integrated circuit, which is our controller. Our controller is calculating control vectors in nanoseconds internally. We run a complete ARM4, which is a very advanced processor within our ASIC. So you're doing complete mathematical computations and you run a predictive system. You predict what the output should be. And we calculate that in nanoseconds. We compute those in nanoseconds. So what's the advantage of that single stage? So we go from low voltage DC to full 220 volt AC in one shot. So the advantages are our component count is very low. We have a little over 300 components in our device. When your component count is very low and you can over specify the components, you can make it extremely reliable. And that's the name of the game in this business. You need a very reliable device. The reason you need a very reliable device is because if you think about it, when somebody buys a solar system, they're buying a financial instrument, right? They're buying a bond. They're buying a bond that will pay annuities every month for the next 20 plus years. So you want a predictable annuity payment. That's when the value of your bond is the highest. So you want a solar system that's extremely reliable. So coming back to the design, we are a single stage power conversion, very few components. And the reason why we have very few components is because of our ASIC. We keep adding, because it's a digital topology, we keep adding more and more functionality into our ASIC. So more and more of our functionality is done in software. So if you think about it, look at the value that we create in terms of reliability, in terms of supply chain issues, right? We make one device completely software defined. So if you're in the US, 240 volts, 60 hertz, line to line, we configure that in software. If you're in California, if you're in Hawaii, if you're in Florida, if you're in Puerto Rico, the grid connection requirements are completely different, all done in software. If you're in Europe, 230 volts, 50 hertz, same thing, line to neutral, we just configure it in software. It's the same device. And same thing with Brazil, 220 volts, same thing, all done in software, right? We reconfigure the device all in software. The firmware is different, but the fundamental hardware is the same. So what that does is it gives us incredible power in terms of managing the supply chain. We make one device, we make a lot of it, right? We are doing about 1 million a month, a million a month of these micros. And so we manage our supply chain very, very well. That's why look at the world we live in today with all of these supply chain challenges. And here we are, Enphase is doing much better than anybody else in the industry in terms of supply chain. And by the way, here's the other really important thing is the devices have become very, very complex. And this is a really interesting evolution, if you may, on how what we have done has evolved over time, right? For example, when we first started the company in 2008, when you think about what an inverter does, 80% roughly of what it was doing was power conversion, DC to AC. But fast forward to today, it's not the case. Today, the actual power conversion function that it does is probably only 30% of what it does. The remaining 70% is at how it interfaces with the grid. How, the complex, and then how it not only interfaces with the grid, but also provides functionality, what I call advanced grid functions that actually support the grid. How it interacts with the rest of the system and how it interacts with the rest of the network. And the power of what we have done is all because of semiconductor single stage power conversion, advanced materials, software defined devices, and a hyper networked system. Everything is networked for us. So we actually took it a step further. We can talk about energy storage as well. The device, the microinverter that we have designed, not only is it software defined to connect to and act like an inverter to connect to anywhere in the world, it's also fully bidirectional. So not only does that device do DC to AC, but it can also in milliseconds switch into AC to DC. So we use the exact same device in our battery as well. So when you connect the device on the roof, it does DC to AC only. When you connect it inside the battery, it does DC to AC to discharge the battery and AC to DC to charge the battery. We'll talk about storage. We'll talk about the evolution from solar to energy, which is a really fascinating evolution and how the world's changing there in a few minutes. Yeah, but that's the key.
Sure. Just one thing that came up in my mind when you were talking, Raghu, about this, we have this software being the big part of it. And you talked about reliability as well, right? Like when I want to validate a reliability of a hardware, I put inside of a chamber, I change temperatures like humidity and shakers, stuff like that. How do you validate the reliability of a software? Can you tell us about that?
Yeah, I would start with software, and then we can talk more about the hardware, right? In the software case, there are actually two elements. You're the first person who asked me this question, and it's a fantastic question, by the way. So in software, for example, software is tightly coupled to the hardware, right? So in the case of software, we have two parts to the software, if you may, within the inverter. There is the part of the software that is all about safety, right? For example, anti-islanding is a safety requirement, right? Which means, you know, I'm not accidentally injecting power into a tank, for example, or into a situation where the grid is, you know, when the grid fails, I'm supposed to turn off. By the way, we'll talk about how we have cracked the code on that. But anti-islanding meaning when the grid fails in a grid tight system, I need to turn off, right? That's a safety requirement. And we comply to a standard called UL 1998. And they partition the code, and that partition code is tested specifically with a pretty extensive test criteria to ensure that the safety functions are very, very well defined. The rest of the performance functions, that's for us to ensure that it's good. So we have, if you look at the way our what we call as a product life cycle process works is engineers develop. So first we define precisely what the product is. So for Brazil, we said, okay, here are what the product requirements are. So we gather data from the field. Then we do the development. In our case, the hardware is the standard. Then we develop the right software in it. And then we do something, engineers do something called design verification and test, DVT. So they test it at the unit level. And they test both the software and the hardware. In our case, hardware is pretty standard. So mostly their testing is the software to ensure that you pass all the test criteria that you have created. The first thing we do, even before we actually start developing the product, is we write a test plan, very detailed test plan. Here are all the conditions we are testing. And by the way, you can imagine we are in generation 8 of our product. So the test plan that we had in 2008 when we did our Gen 1 product, very different from what we are doing today. It's substantially enhanced. And I'll give you some very interesting examples there as well. Then once the unit is tested, then it goes through the hardware testing while the software is in running, because we run the inverter when we are actually testing the hardware as well. So there is no separate testing. It's all hardware and software tested together. And then we also do something called as SVT, or system verification test. So we take not just one device, we take tens of devices, put them all and simulate a complete system. And there we do, again, run through a whole series of tests. So now let me talk a little bit about the hardware testing. Our hardware testing is like nobody else does what we do. And I'll explain what that is. And I know that for a fact. We do something called as temperature cycling, as an example, right? So we take our devices, we take about 250 of our devices, and we have these massive, like a room. It's like a room. You walk into a room, there are 250 of our micros installed in these rooms. And we temperature cycle from minus 40 degrees Celsius to plus 85 degrees Celsius, right? And we temperature cycle that 600 times while the inverter is running at full power, right? And that test takes about 100 days. So it's 3 months you're temperature cycling these devices. We take those inverters, and then we put them in a chamber, another chamber, the same size. And we've got, by the way, a dozen of those, 12 of those massive chambers. And we run what's called damp heat. So we do 85 degrees C, 85% humidity. And we run those for 100 days. We'd run those for 1,500 hours. So basically, if you look at it, because of the number of systems we run, we have 1 million hours of testing before we say the design is okay. And that's called reliability demonstration test. In addition, we also do something called as long-term reliability testing. LTR testing is we look at, we take, for example, we'll take 4 of these devices. We'll put them inside a pressure cooker. We fill the pressure cooker up with water. And then we pressurize it to simulate 1 meter depth of water. We run the inverter at full power underwater, which is under 1 meter of water for 21 days, while we cycle from -40 C to 85 C, right? And what we are looking for is any water getting into the device? We look for water ingress. Our device is completely encapsulated. So we put a silicon-based potting compound inside the device. So when you open our device, you actually don't see components, it's all encapsulated. So you get better thermal performance and you get and very low water ingress. So that's the reason why our entire system, not just the inverter, but the inverter, the connectors, the cables, everything is rated for IP67 or IP67, NEMA 6, as we call it in the US, or NEMA 6P. And that simulates, because we test it for 21 days underwater. We also take all of the components we're looking at. We have material testing. So we put it on a xenon, we put it inside a xenon chamber. A xenon chamber simulates 1,000 suns. So we look at how UV radiance is going to impact any of the materials. So we do incredible amount of hardware and software testing as well. By the way, the software testing is not just on the device. We also test the cloud. We have, and in the cloud, we use microservices and APIs. And so because we use microservices, everything is treated as a microservice. We can isolate failures. It's an example. If you really expand the thinking, it's like a distributed architecture or a decentralized architecture, because it's not one monolithic cloud, right? It is a bunch of services. So if you do have a problem, you can easily identify a particular problem in that particular service and then fix it, right? So it's a fascinating thing when you think about how this world more and more is going to become distributed, not centralized. We'll talk about how we are in a very unique world today when it comes to energy.
Right. And Raghu, when you had the launch of the microinverter, I guess that's the installers, end customers, designers were surprised about that. And it's new. Everything new attracts our attention, but on the other side, it brings some how can I say, some thoughts, like some questions. Is it gonna work well, and things like that? So you were there, so tell us about how it was when you first introduced the microinverter technology, and if you can also talk about the path that Enphase has walked through from that time until today.
So let me start. You're correct. When you first introduce something new, I've come to realize that there are two categories of people. And the one category are the early adopters. They love new technology, especially if it's really cool technology. Look, we were one of the first guys to build a full software stack, networking, communications technology, networking, cloud. We were really the first guys to do it. So here we were. I remember launching the product, being at a show, and we were mobbed. Everybody wanted to come see us because for the first time, they were seeing this beautiful software. Even at the time, we didn't have an app. I think, we had just barely had an app. And you could see performance of your module on a per module basis, on a per panel basis. And we could talk to it, we could query it. People were just blown away. So there was a category of people who loved it and said, I cannot wait to try this out. And then there was a category of people that said, oh, it's brand new technology. Yes, it's Silicon Valley technology. These guys know what they're doing. They're high tech, but I'm going to wait, right? What I gathered from all of that is, and what I've realized over time is our installer partners are the best filters for good and bad technology. Because when you think about our customers are the long tail installers. For them, customer service, reliability and customer service, simplicity matters the most, right? Because what do they want to do? They want to come to a site, they want to install it. It should be very simple to install, all plug and play, do it very quickly, and then leave. And never have to think about that site again. Because why? The thing is very, very simple. I'll say something here. I've internalized this over my entire career. It's very easy to make things complex. Very easy to build a complex system. Actually, it's very complex and very hard to make a simple system. It takes a lot more ingenuity and thinking. Complexity is not the friend of reliability. Simple systems can be made very simple, very, very reliable. So if you go talk to our installer partners and ask them, what is it you like most about Enphase? The first thing they'll tell you is it's very simple. But simplicity is very, very complicated to do and to make. Takes a lot of innovation, incredible amount of innovation. And comes with that, when something is very, very simple, what comes with that is reliability. So for our customers, it's about making things very simple, making things very reliable, and providing the best customer service. If you do that, if you take care of your partners well, hey, it's over, you win. And that's what we have done both here what we have done here in the US, demonstrated very, very well. If you do that, if you take care of your partners, you'll win. So initially, there were a bunch of early adopters. They loved our system. They were good to go. But then others were wait and see. I need to wait. And we were like, that's perfectly okay. And as we proved our reliability, they became our customers. And now we have extremely loyal customers. I'll give you one example of reliability also, which I meant to talk about in the previous section. The grid is a very harsh environment, right? Especially if there's a storm or something like that, voltages fluctuate all over. If there's lightning, you can have induced voltages. The grid is very harsh. So, in the winter, when there's a storm, you have something called line slaps. Your, two lines will touch each other momentarily, and your phase reversals and all kinds of crazy waveforms. The load in your house really doesn't care about that because you have a power supply and a filter and so on and so forth. Inverters are injecting power into the grid, and they're a current source. They care a lot, right? So what we have done over time is we have built a library of very, very complex grid events. So we've taken all of these grid events and we've built this massive library. So anytime we test a product, we know, and by the way, over time, we keep collecting new events. So same thing when we have entered Brazil. I'm sure the Brazilian grid is going to be, I know for a fact, Brazilian grid is going to be different than a grid in Netherlands, as an example. So what we are doing is collecting these waveforms, understanding what, and then we bring it back into the office, into our reliability lab, and then we synthesize more waveforms based on the shape that we see. And then when we test the inverter, particularly the inverter software, your previous question, we see how does the inverter react? How does the software in the inverter react when it sees such an event? Usually those events will last for only a couple of cycles, and then it'll go back to normal. And we protect ourselves when that happens. So design, so anyway, when you think about what our customers want, they want simplicity, they want reliability, they want amazing customer service.
Right. Raghu, I got to know Enphase, I would say like we are now in 2022, I would say 7 to 8 years ago, okay? I saw that in the for the very first time in a catalog that I got from from US, from the market in US. And in the PV system, there were a lot of Enphase optimizers and microinverters. And I was always questioning myself when Enphase would come to Brazil, and I bet that quite a few professionals in Brazil had the same question. So the question is, why it took so long for Enphase to arrive officially in the Brazilian market?
Yeah, it's a wonderful question. You know, we needed to make sure. Look, we are in this business for the long run. You know, I want to build a company that's 50 years, great company that'll last 50 years, 100 years, right? So for us, it was making sure that we are building great products that our customers love. And part of that means building great microinverters, very reliable microinverters, and very simple to install kind of microinverters. And we needed to prove that out. We needed to prove that first in the US, and which we did. Today we have, you know, we are probably the number one inverter company in the United States. You know, and it's because of the reasons that I said. We really needed to make sure that we had proven our technology, and that doesn't happen overnight. It takes 8 years, 10 years to do it, which we have done it, and we have made it better and better, right? And here we are on generation 8 of our product. You know, we have, with IQ8 as an example, we have done something that I think is transformative, right? As an example, what I mean by that is, let me spend just 30 seconds on IQ8, and then I'll talk about, close out why it took us this much time to come to Brazil. IQ8 is a phenomenal new technology. All solar inverters today are grid tied, right? What we have, and you know, the problem with grid tied inverters is if the grid fails, the solar system is down. This problem, it's a problem. It doesn't fulfill the promise of solar, right? This problem became very stark when Hurricane Maria hit Puerto Rico in about 3 years ago. We had, at the time, including Enphase, there were probably 20, 30,000 solar systems in Puerto Rico. And when the hurricane hit, and you know, the storm was a couple of days, and then after that was bright sunshine, but the grid was down and none of the solar systems were operating. And that is wrong, right? That shouldn't happen. And so with IQ8, we have cracked the code on how to allow a solar system without energy storage, without a battery, to sustain itself, to continue operating, even in the absence of a grid. If the grid's there, great. If the grid's not there, great. We'll convert all the available energy, all the available irradiance into usable energy. And that's a huge deal. And I cannot even imagine how that would have helped people in Puerto Rico who were without a grid for 1 month, for 1 to 2 months. And they could have had a solar system without batteries that were still operating. And at least during the day, you could cool your food, you could do some, you would have, you know, enough, you could pre-cool your house, you could cook, you could do a bunch of things if that was possible. So a lot of the things that we do in the US, we do it in the US first so we can develop the technology, prove out the technology, and then we can take it to the rest of the world. So that is really honestly the reason why we are not in Brazil. I always knew that Brazil, it made sense for Brazil. There's a lot of sunshine. It's a perfect place for solar. And so the market was going to develop. There was no question. And here we are. I think I've heard anywhere from, like, you know, it's a multi-gigawatt market for residential. It's perfect. And it's a perfect market for Enphase. And we needed to make sure that we had amazing technology, all developed, the easiest to install, very reliable technology, and before we came to Brazil. And you know, things like IQ8, which in our view is transformational technology.
Right. Let's talk about safety. We explored this a little bit, but let's talk about more this. Do you think that the same law and code that we have today in USA is going to be adopted in Brazil?
It should be. Let's start there. It should be adopted. It makes sense, right? If you look at a number of countries, look at Australia, now look at Europe, they're all waking up to the fact that solar systems can be made more safe, right? Can you imagine how bad it would be? I mean, everybody loses if a solar system is not safe, right? And if you look at when you're dealing with high voltage DC is simply, it's a physics problem, right? When you have high voltage, especially when it's DC that is not varying like a sine wave, which is what an AC does, where it goes through 0 volts. When you have high voltage DC, it is prone to arc faults. You know, people talk about, oh, I'll have, there are standards now called arc fault detection, etc. It's an unbounded problem. You'll never completely solve it. You have to solve it architecturally. These kind of arc fault detection circuits and all of those are all band-aids. Solve the problem architecturally. You need to be what's called correct by construction. If you're architected right, stay in the low voltage world, DC world, and move everything into AC. AC is intrinsically much safer than high voltage DC, right? So Brazil must adopt safety, because it's not good for the homeowner if something bad happens. It's not good for the solar industry. And if something's not good for the solar industry, it's not good for the world. Now's the time when we need to have extraordinary effort to enable solar in this world. We are in a very precarious position when you think about the things that are happening with regards to climate change. I was just reading today in California, there's some bad news and good news. The last 22 years, the drought that we are having here in Northern California in the last 22 years hasn't happened in the last 1,000 years. That's what the research shows. Climate change is real. Climate change is intense, and climate change is not happening gradually. Climate change is happening abruptly. 22 years is not a long time. And here we are, things that have happened in the last 22 years hadn't happened in the last 1,200 years. But we have the technology. We have the technology to slow down and stop climate change. So don't put any barriers, don't create any barriers for the adoption of solar. This is about the world, right? Not just about Enphase, it's about the world. Don't get in the way. And safety is an example of that. So I gave you some bad news. Here's some amazing news. Last week, for about a 15-minute period in California, 102% of the demand was met by renewables, solar, wind, and hydro. Very little hydro, solar and wind. 102% of California's demand. By the way, California is like a 40 gigawatt grid. It's massive. 102% of the demand for 15 minutes about a week ago was met by renewables. Wow, fantastic, right? That brought a big smile to my face, that it can be done. If you have the mind for it, you can do it. And of course, coming back to safety, you cannot do anything that would jeopardize the deployment of solar. And I mean, kudos to Brazil for the amount of solar you guys are deploying. Amazing, amazing. Congratulations. And nothing should come in the way. And we just need to keep, it's our responsibility. Enphase companies, it's our responsibility to bring technology to the market that is better performance, lower cost, more reliable, and of course, very, very safe, right? So again, I say this, Brazil should adopt higher safety standards for solar, no question, right?
That is correct. And Raghu, what about next inventions? What we should be expecting from the Enphase? What are the areas that your R&D guys are focusing today, where you're putting your money on? Like we talk about batteries, hydrogen, you talked about IoT. Tell us about that.
Absolutely. You know, the world's transforming in a very big way. I've said this before, we are in a seminal moment in time when it comes to energy and energy infrastructure, right? It's a moment in time, and I say this with great humility, but I really think that I hope you remember this conversation 10 years from now. And you will note that 2021, 2022, this time period was a moment in time where a lot of things changed in this world from an energy infrastructure point of view. You're seeing utility rates going up. Somebody was mentioning yesterday that average utility rate in Europe has gone up by 70%. US utility rates have gone up by 20-30%. UK 30%. These are big numbers, and it's because the feedstock, which is, you know, fuel has gone up, costs have gone up a lot. Utilities are having to invest significantly in hardening their grid because of climate change issues. You know about the fires in California and what some of our utilities have to do. I think they're investing $10 billion in underground, making transmission lines underground. $10 billion is a drop in the bucket of what's required. Utility rates have gone up. Second is geopolitical issues, right? Look at the war in Ukraine as an example. All countries are now suddenly starting to think about energy security, right? When nations think about energy security, it very quickly translates to people thinking about energy security. Third, you're seeing, and a good thing is a massive amount of EV deployment, right? EV is growing at a CAGR of 40% in the US, 25% in Europe, off of a very small, much larger base, right? Like home electrification in general, people are moving away from gas heating to heat pumps. All that means is you're going to double your demand, more than double your home demand, right? So I have utility rates going up. I have to think about energy security at the home level. I have my own demand going up by 2x to 3x because of EVs and electrification. How do I meet this demand? How do I solve this problem? And I honestly believe it has to be done through what are called distributed energy resources, DERs. That's behind the meter energy systems, not just solar, behind the meter energy systems. And when I say behind the meter energy system, it means solar. Solar will always be the hero of the show. It's got to be solar. It has to be storage. It has to be load management, heat pumps, EVs. All of that means I turn my home into and provide. I manage all of these disparate resources, right? Solar, storage, loads, EVs, heat pumps, the grid itself, everything. I'm managing those through an energy management system. And I have the ability to create a microgrid out of my house, right? That is a great evolution. Think about the value that you bring when every home is a very resilient, self-reliant microgrid, right? But I'm basically, and now what I have the ability, and if you do everything in the AC domain, which is what we do, we use an AC architecture, we create this AC bus, and then you connect all of these things in the AC domain, and then let our technology, and the technology we have is called Ensemble, that technology manages what's the best way to flow, to it federates the energy flow, the electron flow from different resources. Should I be using solar at this time? Okay, if I don't have solar, should I use my storage? Should I use my grid? Should I turn on my washer dryer? Should I turn on my heat pump? What about my EV? Can I discharge my EV? Can I charge my EV? Everything. That's the technology that we are well along our way in developing. This is a transformation. And if you think about it, if I have a microgrid that's extremely intelligent, comes back to the original thinking of a distributed architecture, where endpoints are making more and more intelligent decisions. Now I can connect multiple microgrids together and create even more value. I can start transacting energy from one home to another. The infrastructure already exists. The utilities already have that infrastructure, right? I can send energy back and forth from one home to another by leveraging utilities' existing infrastructure. What you're effectively doing is you're recreating the grid from the inside out. You're rebuilding the grid from the endpoint, which is extremely intelligent. I've said this before, and I'll say it again. If Thomas Edison, 125 years later, was walking down the streets of Brasilia, probably, and he looked up, he would probably recognize all elements of the energy infrastructure. He would recognize the poles, the distribution center, the poles, the wires, the meters, everything. Nothing has changed in 125 years. It's time. The world has changed. The world has changed. You're dealing with utility rates going up, geopolitical issues, wars, climate change, everything. EVs, we have to rethink how we think about delivering energy to the homeowner, right? So it's a transformative world, and that's what we are working on, is building this energy system that can manage all the different types of resources within the home and build a very resilient, self-reliant microgrid for the home, and give you the ability to network all of these microgrids together. So when a homeowner thinks about, I'm making an investment in solar, they also have to think about, where is it going? So that's why I think about, you have to think about the company, you have to think about what they are thinking, what is their thinking, because it's not just solar and you're done. Over time, you have to do, the world's moving where other things are coming. EVs, you're going to go buy an EV in the next 6 months. How are you going to charge your EV? The utilities doesn't have the ability to charge your EV. There's a bottleneck. They just don't either have sufficient generation. Even if they have sufficient generation, can't deliver it to the homeowner. And what happens if multiple people on your street have EVs? You're going to easily overload your infrastructure. So we are in the midst of major transformation. And this is a seminal moment in time when it comes to energy.
Right. Raghu, I would be talking to you like a day in a row, a week. It's been an amazing conversation. But to finish, for those who are betting every day on the solar market, like installers, designers, service providers, distributors, all those enterprises, what would be your very best advice for them?
Sorry, my very best advice? Yes, they're in a very noble business. This is not just a business. This is about making sure that we leave the world for our children better than how we were handed the world. And we are in a business where we can really make a big difference in this world. And companies like Enphase have the technology. We have the technology. We are not waiting for anything. The technology exists to make fundamental changes in how we think about energy. And it's not just about the business and making money. All that is important, very, very important, because you can't change the world without having a healthy business. But we have the technology, we have the wherewithal, and it's really required. We don't have a choice. It's a moral obligation. And And so when you think about companies like Enphase, we really believe strongly that we take what I just said very, we think that's very important. And we think that we have built the technology that can be transformative in this world. And so it's not just about, oh, I installed solar and go away. It's about thinking long-term, right? This is not one thing and done. And so we take what we are doing, we take our business very, very seriously because it's important.
Very good. Raghu, is there anything that we didn't talk about that you would like to talk a bit?
No, I think first and foremost, thank you for giving me this opportunity to share my thoughts. Like I said, we are in a very critical point in time, and I think we at Enphase have the technology that we can really make a difference. And Brazil is a phenomenal market, and phenomenal market. You guys have done something that I think no other country in the world has done, which is grow a residential market as fast as you have. And we are investing heavily in Brazil. We have a phenomenal team in Brazil, and we'll continue to grow the team. And we really take the Brazilian market very seriously now.